At the center of the Milky Way galaxy, 26,000 light-years from Earth, within a region spanning less than a single light-year across, more than 100 massive stars orbit through space at velocities that exceed 1,000 kilometers per second, their trajectories shaped by the gravitational influence of Sagittarius A*, a supermassive black hole containing the mass of 4 million suns compressed into a region smaller than the orbit of Mercury. This central parsec of the galaxy represents one of the most extreme environments accessible to astronomical observation, a place where the fabric of spacetime curves so severely that light itself bends in transit, where stellar winds collide at relativistic velocities, where the density of matter reaches levels found nowhere else in the galactic disk. The gravitational potential well at the galactic center is so deep that escape velocity exceeds 1,000 kilometers per second, meaning that any object moving more slowly than this velocity remains gravitationally bound to the region, trapped in perpetual orbit around the supermassive black hole. The stellar density in the innermost regions reaches values exceeding 10 million stars per cubic parsec, a concentration approximately 1 million times higher than the stellar density in the solar neighborhood, creating an environment where stellar collisions and close encounters occur with sufficient frequency to significantly affect stellar evolution and dynamical processes. The radiation field in this region, generated by thousands of massive luminous stars, exceeds that of the solar neighborhood by factors of millions, bathing everything in intense ultraviolet and X-ray radiation that strips away gas from molecular clouds, ionizes atomic hydrogen across vast volumes, and heats dust grains to temperatures where they radiate predominantly in the infrared. Within this crowded stellar cluster, among the luminous giants and the fast-moving S-stars that complete their orbits in mere decades, astronomers have identified a peculiar object designated GCIRS 13E, a source of infrared radiation whose properties suggest something far stranger than another massive star, something that challenges existing models of how black holes form and grow, something that may represent a missing link in the evolutionary chain connecting stellar mass black holes to their supermassive cousins. The nature of GCIRS 13E remains uncertain, debated, investigated through multiple wavelengths and theoretical frameworks, but one possibility stands out with particular significance: the prospect that this compact infrared source harbors an intermediate mass black hole, an object containing perhaps 1,000 to 10,000 solar masses, hidden within the chaotic environment of the galactic center, slowly spiraling inward toward an eventual merger with Sagittarius A** itself. This hypothesis, if confirmed, would solve multiple outstanding puzzles in astrophysics simultaneously, providing observational evidence for a class of objects whose existence has been predicted theoretically but never definitively confirmed, explaining certain anomalies in the dynamical structure of the galactic center stellar cluster, and offering a window into the processes by which supermassive black holes grow and evolve over cosmic time. The implications extend beyond the Milky Way to galaxy formation throughout the universe, to the gravitational wave signals that future detectors will observe, to fundamental questions about how structure emerges and develops in the cosmos from initial conditions set during the first moments after the Big Bang. The galactic center presents observers with fundamental challenges that complicate every measurement, every inference, every attempt to understand the nature of individual objects within its boundaries. Between Earth and Sagittarius A** lies the entire breadth of the galactic disk, 26,000 light-years of interstellar dust and gas that absorbs and scatters visible light so completely that optical observations reveal almost nothing of the region's structure, transforming what should be the brightest point in the night sky into an area of apparent darkness, a zone of obscuration that hides the galaxy's heart from direct view. This extinction, quantified by astronomers as approximately 30 magnitudes in the visible spectrum, means that only one photon in 10 trillion manages to traverse the intervening space without being absorbed or redirected, an attenuation so severe that it renders traditional optical astronomy essentially useless for studying the galactic center's detailed architecture. The dust responsible for this extinction consists primarily of silicate and carbonaceous grains, microscopic particles typically 1/10 of a micrometer in diameter, produced through stellar mass loss from evolved stars, expelled into the interstellar medium where they accumulate in molecular clouds and diffuse regions throughout the galactic disk. These grains scatter and absorb shorter wavelengths more efficiently than longer wavelengths, a phenomenon described by Rayleigh scattering and Mie theory, explaining why blue light suffers more extinction than red light, and why infrared radiation penetrates dust more effectively than visible wavelengths. Infrared radiation, with its longer wavelengths ranging from 1 to several micrometers, penetrates this dusty veil more effectively, allowing astronomers to peer through the obscuration and observe the stellar populations, the gas clouds, the complex dynamics unfolding at the galaxy's gravitational focus. The development of infrared detector technology, beginning with single-pixel photometers in the 1960s and progressing through modern large-format array detectors containing millions of pixels, revolutionized galactic center astronomy by opening observational access to this previously hidden region. Ground-based infrared observations must contend with Earth's atmosphere, which absorbs infrared radiation at most wavelengths through molecular absorption by water vapor, carbon dioxide, and other constituents, limiting ground-based observations to specific atmospheric windows at wavelengths around 12, 16, 22, 35, and 48 micrometers, designated by astronomers with letters J, H, K, L, and M respectively. Observations at longer infrared wavelengths require space-based telescopes that operate above the atmosphere, platforms like the Spitzer Space Telescope and the James Webb Space Telescope that can observe at wavelengths extending to hundreds of micrometers where thermal emission from dust becomes dominant. Even in the infrared, extinction remains significant, reducing observed brightness by factors of tens to hundreds depending on wavelength, requiring careful calibration and correction to infer intrinsic source properties from observed magnitudes. Radio waves pass through interstellar dust even more freely, revealing structures invisible at other wavelengths, while X-ray observations capture the signatures of high-energy processes, the hot plasmas and relativistic particles that populate this extreme environment. Radio astronomy at the Galactic Center has revealed the compact radio source Sagittarius A*, discovered in 1974 through observations at 21 cm wavelength, subsequently observed at progressively shorter radio wavelengths and higher angular resolutions, culminating in the Event Horizon Telescope observations that produced the first direct image of the black hole's shadow in 2022. These radio observations detect synchrotron radiation from relativistic electrons spiraling in magnetic fields near the black hole, emission mechanisms that produce characteristic spectral signatures allowing astronomers to distinguish thermal from non-thermal processes, to measure magnetic field strengths through polarization observations, to probe the immediate environment of the event horizon at scales approaching the Schwarzschild radius. X-ray observations from satellites like Chandra and XMM Newton detect emission from gas heated to temperatures exceeding millions of degrees, whether through shock heating where stellar winds collide, through accretion onto compact objects where gravitational potential energy converts to thermal energy, or through reflection of X-rays from Sagittarius A** off surrounding molecular clouds, creating light echoes that reveal the black hole's past activity during epochs when it accreted more vigorously than in the present quiescent state. Each wavelength reveals different aspects of the galactic center, each observational technique provides complementary information, and astronomers must synthesize data across the electromagnetic spectrum to construct coherent models of what exists in this distant, hidden realm. The process of multi-wavelength astronomy requires careful registration of images from different telescopes, aligning coordinate systems with precision sufficient to identify the same source across datasets, accounting for differences in angular resolution, in sensitivity, in the physical processes that dominate emission at different wavelengths. A single object like GCIRS 13E might appear bright in the infrared, faint or undetected in radio observations, and entirely invisible in X-rays, not because it lacks emission at these wavelengths but because the sensitivity limits of available telescopes place its emission below detection thresholds, or because intervening material absorbs the radiation before it reaches Earth, or because the physical conditions in the source simply do not produce significant emission through the relevant mechanisms. Interpreting these non-detections requires as much care as analyzing positive detections, understanding what limits can be placed on source properties based on the absence of observed signal, using theoretical models to predict expected emission levels and comparing these predictions against observational constraints. The uncertainty inherent in these observations, the limited information content of faint infrared sources observed through obscuring dust across enormous distances, means that multiple theoretical interpretations often remain viable, requiring additional observations or new theoretical insights to distinguish between competing explanations. The stars orbiting Sagittarius A** have provided the most direct evidence for the supermassive black hole's existence, their precisely measured trajectories revealing the presence of an enormous gravitational source confined to a remarkably small volume of space. Beginning in the 1990s, teams of astronomers initiated systematic monitoring campaigns using infrared adaptive optics systems on large telescopes, tracking individual stars as they moved through the crowded central region, measuring positions with millisecond precision, accumulating data points year after year until orbital patterns emerged from the accumulated observations. Adaptive optics technology, developed to correct for atmospheric turbulence that blurs astronomical images, uses deformable mirrors whose shapes change hundreds of times per second in response to measurements of wavefront distortions, effectively removing the twinkling and blurring that limits the resolution of ground-based telescopes, allowing diffraction-limited observations where image sharpness reaches the theoretical maximum determined by the telescope's aperture diameter. This technological advance transformed galactic center astronomy, enabling the resolution of individual stars in regions where previous observations detected only blended, confused emission from multiple unresolved sources. The monitoring programs conducted by teams at the Keck Observatory in Hawaii and the Very Large Telescope in Chile accumulated observations spanning decades, creating datasets containing thousands of position measurements for dozens of stars, orbital solutions computed through least squares fitting to Keplerian models, uncertainties quantified through statistical analysis of measurement residuals. The so-called S-stars, designated with numbers like S2, S62, and S4714, follow highly eccentric elliptical orbits around Sagittarius A**, their periastron passages bringing them to within a few light-hours of the black hole's event horizon, their velocities at closest approach reaching significant fractions of light speed. S2, perhaps the best-studied member of this stellar family, completes its orbit in approximately 16 years, its path traced with such precision that astronomers can measure relativistic effects predicted by general relativity, the gravitational redshift of the star's light as it climbs out of the black hole's potential well, the precession of its orbit as spacetime curvature affects its trajectory. At periastron, S2 approaches to within 17 light-hours of Sagittarius A**, corresponding to roughly 200 times the radius of the black hole's event horizon, reaching velocities approaching 8,000 km per second, nearly 3% of light speed. At such velocities, relativistic effects become measurable, the star's light blue shifted as it approaches Earth during part of its orbit and redshifted as it recedes, these Doppler shifts superimposed on the gravitational redshift caused by photons climbing out of the black hole's potential well. The gravitational redshift, a prediction of general relativity confirmed in laboratory experiments and through observations of white dwarfs and neutron stars, causes photons to lose energy as they escape from regions of strong gravitational field, their wavelength stretching toward redder colors by an amount proportional to the depth of the potential well. For S2 at periastron, the gravitational redshift reaches approximately 200 km per second equivalent velocity, a small but measurable effect when combined with the star's orbital motion, requiring careful spectroscopic analysis to disentangle the various contributions to observed wavelength shifts. The orbital precession of S2, another relativistic effect, causes the ellipse's long axis to rotate slowly in space, completing a full rotation in approximately 100,000 years according to general relativistic calculations. Although this precession rate seems small, several orders of magnitude less than the famous precession of Mercury's orbit that provided early evidence for general relativity, the accumulated effect becomes measurable after multiple orbital periods, with current observations showing agreement with general relativistic predictions at the few percent level. These measurements test Einstein's theory in a regime far stronger than accessible in the solar system, where gravitational fields remain weak and relativistic corrections amount to tiny perturbations on Newtonian orbits, providing confidence that general relativity correctly describes gravity even in the extreme conditions near supermassive black holes. Other S-stars follow different orbits with varying periods, eccentricities, and orientations, their collective properties revealing the structure and mass distribution of the galactic center environment. S62 holds the current record for closest approach to Sagittarius A**, passing within 16 light-hours during its periastron in 2019, reaching velocities exceeding 10% of light speed, experiencing even stronger relativistic effects than S2. S4714 follows an even more eccentric orbit with a period of approximately 12 years, its velocity at periastron potentially exceeding 25,000 km per second based on preliminary orbital solutions, though uncertainties remain because fewer orbital cycles have been observed for this recently discovered star. The distribution of orbital elements among the S-stars reveals important information about how these objects came to occupy their current trajectories, whether they formed in place through star formation in a disk around Sagittarius A*, or migrated inward from larger radii through dynamical interactions, or scattered into their current orbits through close encounters with other massive objects. Statistical analysis of the orbital plane orientations shows no strong preference for a single plane, suggesting that the S-stars do not represent a coherent disk but rather a more spherically distributed population, consistent with relaxed stellar dynamics where gravitational scattering has randomized orbital inclinations over time. The mass distribution among the S-stars, inferred from spectroscopic observations that measure surface temperatures and luminosities, indicates that most are relatively young massive stars, B-type main sequence objects with masses ranging from 5 to 20 times the solar mass. Stellar populations that should have lifetimes of only 10 to 100 million years before exhausting their nuclear fuel and evolving off the main sequence. These observations confirm not only the presence of Sagittarius A*, but also its extraordinary compactness, the concentration of 4 million solar masses into a region no larger than the distance between the Sun and Mercury, a density that leaves no plausible explanation other than a black hole, an object whose escape velocity exceeds the speed of light, whose gravitational influence dominates everything within several light-years. The precision of orbital measurements allows astronomers to place upper limits on the physical extent of the central mass, confirming that it occupies a region smaller than a few light-hours in radius, far more compact than any normal stellar cluster or other conventional astrophysical structure could maintain without collapsing under its own gravity. Alternative explanations invoking exotic forms of matter, hypothetical particles, or modifications to gravitational physics have been proposed but struggle to match the full range of observational constraints, from the stellar orbits to the radio and X-ray properties of Sagittarius A** itself, leaving the supermassive black hole interpretation as the only viable explanation consistent with all available data. The mass of Sagittarius A** determined from stellar orbits, approximately 4.1 million solar masses with uncertainties of a few percent, agrees with independent estimates based on the dynamics of gas clouds, on statistical analysis of the broader stellar velocity distribution, and on theoretical predictions relating supermassive black hole masses to properties of their host galaxies, providing confidence that this fundamental measurement accurately characterizes the galactic center's most dominant object. Within this population of central stars, GCIRS 13E occupies an unusual position both physically and observationally, appearing in infrared surveys as a relatively faint source located approximately 13 arcseconds, or roughly half a light-year in projection, from Sagittarius A** itself, moving through space with a velocity measured at approximately several hundred kilometers per second relative to the local standard of rest. The designation GCIRS 13E reflects its discovery through infrared observations, the letters and numbers encoding its place in catalogs compiled during systematic surveys of the galactic center region conducted in the 1990s and early 2000s, when infrared detector arrays first enabled imaging of the crowded central parsec with sufficient resolution to distinguish individual sources. The prefix GC denotes galactic center, IRS indicates infrared source, and the number 13E places it within a particular survey field and catalog sequence, a naming convention that reveals nothing about the object's intrinsic nature but serves to identify its location on the sky and in observational databases. The position of GCIRS 13E at half a light-year projected distance from Sagittarius A** places it within the region of strongest gravitational influence, where orbital velocities remain high, where dynamical timescales span hundreds to thousands of years, where the stellar density reaches extreme values that facilitate frequent gravitational encounters between objects. Initial observations characterized it simply as another infrared source among many, unremarkable except for its position within the central cluster, but subsequent studies began to reveal peculiarities that set it apart from ordinary stellar photospheres. The infrared spectrum of CIRS 13E lacks the strong stellar absorption features that would indicate a conventional massive star, showing instead a relatively featureless continuum that suggests either a highly dust-enshrouded object or something fundamentally different from a stellar surface. Normal stellar spectra, even when observed through significant dust extinction, retain characteristic absorption lines from hydrogen, helium, and heavier elements in the stellar atmosphere. These spectral features imprinted on the continuous blackbody-like emission from the stellar photosphere, providing information about the star's temperature, chemical composition, surface gravity, and radial velocity. The most prominent stellar features in infrared spectra include the bracket series of hydrogen lines, the helium absorption lines, and molecular bands from carbon monoxide and other molecules in cooler stellar atmospheres, all of which should appear in observations of massive stars at the galactic center if those stars are not completely obscured by surrounding dust. CIRS 13E's spectrum shows none of these features with any significance, its infrared emission dominated by a smooth continuum that rises toward longer wavelengths, characteristic of thermal emission from dust grains heated to temperatures of several hundred to 1,000 degrees Kelvin. The spectral energy distribution of CIRS 13E, constructed from photometric measurements at multiple infrared wavelengths spanning from 1 to several micrometers, follows approximately a power law or modified blackbody shape, consistent with emission from a distribution of dust grains at various temperatures rather than a single temperature blackbody as would be expected from a stellar photosphere. Detailed fitting of this spectral energy distribution requires models that account for dust grain properties, including their composition, size distribution, and geometric arrangement around the central heating source, parameters that remain poorly constrained given the limited spectroscopic information and the faintness of the source. The total infrared luminosity integrated across all wavelengths, estimated at approximately a few thousand times the solar luminosity after correcting for distance and any additional extinction not already accounted for, places CIRS 13E in an intermediate range, too luminous to be a single low-mass star but not as luminous as the brightest massive stars in the galactic center. This luminosity could be explained by a dust-enshrouded star of 10 to 20 solar masses, by a small cluster of less massive stars surrounded by a common dust envelope, by a binary system where interaction between components produces excess infrared emission, or by accretion onto a compact object like a black hole where gravitational potential energy converts to radiation through the viscous heating of infalling material. Attempts to detect the source at other wavelengths have produced mixed results, with no clear optical counterpart emerging from the obscuration, and only tentative detections at radio and X-ray frequencies, leaving astronomers with incomplete information about its true nature. The absence of optical emission is not surprising given the extreme extinction toward the galactic center, but the failure to detect radio emission at levels predicted for various theoretical scenarios provides important constraints on the physical processes operating in CIRS 13E. Radio emission from astronomical sources typically arises through synchrotron radiation from relativistic electrons, through thermal free emission from ionized gas, or through molecular line emission from cold gas clouds, each mechanism producing characteristic spectral signatures that allow observers to distinguish between competing explanations. Observations of CIRS 13E at centimeter and millimeter wavelengths have placed upper limits on radio flux densities that rule out some models while remaining consistent with others, the interpretation depending on assumptions about magnetic field strengths, electron energy distributions, gas densities, and temperatures. X-ray observations similarly have produced only upper limits or at best marginal detections, indicating that if CIRS 13E contains an accreting compact object, the accretion rate must be quite low, insufficient to produce the bright X-ray emission characteristic of actively accreting stellar mass black holes and binary systems elsewhere in the galaxy. The proper motion of CIRS 13E, measured through comparison of infrared images obtained several years apart, reveals that the object moves across the sky at a rate consistent with its inferred orbital motion around Sagittarius A*, though the baseline of available observations remains too short to determine a complete orbital solution as has been accomplished for the S-stars. The measured tangential velocity component, perpendicular to the line of sight, combined with spectroscopic measurements of the radial velocity component along the line of sight, allows astronomers to reconstruct the three-dimensional space velocity and to compare this velocity against expectations for various dynamical scenarios. An object on a typical orbit in the galactic center stellar cluster would move with velocities of several hundred kilometers per second, consistent with the viral theorem relating kinetic energy to gravitational potential energy in gravitationally bound systems. GCIRS 13E's measured velocity falls within this expected range, neither unusually high nor unusually low, providing no strong evidence for exceptional dynamical circumstances but also not ruling out interesting possibilities like recent gravitational scattering or infall from larger radii. Long-term monitoring to determine the orbital parameters precisely would require continued observations spanning decades, during which the object's position would trace out a measurable arc against the background stellar field, eventually revealing the orbital period, eccentricity, and spatial orientation if sufficient astrometric precision can be maintained. The hypothesis that GCIRS 13E might harbor an intermediate-mass black hole emerged from efforts to explain its unusual observational properties within the context of theoretical predictions about how such objects could exist in the galactic center environment. Intermediate-mass black holes, defined somewhat arbitrarily as containing between 100 and 100,000 solar masses, occupy a curious position in the black hole mass spectrum, bridging the gap between stellar mass black holes formed through supernova collapse and the supermassive black holes found at galaxy centers. This mass range remains poorly explored observationally, with fewer confirmed examples than either stellar mass or supermassive black holes, creating what astronomers sometimes call the intermediate mass black hole desert, a region of parameter space where theory predicts objects should exist but observations have struggled to confirm their presence. The lower boundary at roughly 100 solar masses marks the approximate upper limit for black holes formed through standard stellar evolution, where even the most massive stars observed in the present-day universe would produce black holes no heavier than several tens of solar masses after accounting for mass lost through stellar winds and supernova explosions. The upper boundary at 100,000 solar masses represents a somewhat arbitrary division before the supermassive regime begins, though physically it corresponds to scales where the object becomes sufficiently massive that its presence significantly affects the dynamics of its environment, creating detectable signatures in the velocities of surrounding stars or gas. Evidence for intermediate-mass black holes in other astrophysical contexts remains fragmentary and contested, with candidates identified in globular clusters, in the centers of dwarf galaxies, in ultraluminous X-ray sources, but few if any definitive confirmations of their existence. Globular clusters, dense spherical stellar systems containing hundreds of thousands to millions of stars bound together by gravity, represent promising locations to search for intermediate-mass black holes because dynamical processes in these systems naturally lead to mass segregation, where the most massive objects sink toward the cluster center through gravitational interactions, potentially forming a central concentration that could undergo runaway collisions leading to an intermediate mass black hole. Observations of globular clusters have revealed some systems with central velocity dispersions higher than expected from the visible stellar population alone, suggesting the presence of additional mass that could be an intermediate mass black hole, though alternative explanations involving concentrations of stellar mass black holes or measurement uncertainties remain viable. Dwarf galaxies, smaller cousin systems to massive galaxies like the Milky Way, should host smaller central black holes according to the observed correlation between supermassive black hole masses and galaxy properties, predicting intermediate mass black holes in systems with stellar masses of 10 million to 1 billion solar masses. Observations have detected some dwarf galaxies with active galactic nuclei, where accretion onto a central black hole produces detectable radiation, allowing mass estimates that place the central objects in the intermediate mass regime, though the samples remain small and the uncertainties large. Ultraluminous X-ray sources, compact X-ray emitters found in nearby galaxies with luminosities exceeding the theoretical maximum for accretion onto stellar mass black holes, have been interpreted as possible intermediate mass black holes, though this interpretation competes with alternative models involving stellar mass black holes accreting at super-Eddington rates or neutron stars with extremely strong magnetic fields. The Eddington limit, a fundamental constraint on accretion luminosity derived from balancing radiation pressure against gravitational infall, predicts that an accreting object cannot exceed a luminosity proportional to its mass without blowing away the infalling material, setting a maximum brightness for a given black hole mass. Ultraluminous X-ray sources exceed this limit when interpreted as stellar mass black holes, leading to suggestions that they must contain intermediate mass black holes where higher masses allow higher Eddington-limited luminosities, but detailed observations have revealed complexities in the accretion geometry, in the beaming of radiation, and in the possible role of stellar mass compact objects accreting at super Eddington rates, leaving the nature of most ultraluminous X-ray sources uncertain. Theoretical models suggest multiple formation pathways for intermediate mass black holes, including the direct collapse of exceptionally massive stars formed in the early universe, the runaway collision and merger of stars within dense stellar clusters, or the gradual growth of stellar mass black holes through repeated mergers and accretion episodes. The direct collapse scenario envisions formation during the first billion years of cosmic history, when the universe contained pristine gas clouds composed only of hydrogen and helium without heavier elements produced by earlier stellar generations. Such primordial gas clouds, if they could avoid fragmenting into smaller pieces during collapse, might form individual stars with masses of hundreds to thousands of solar masses, far exceeding the typical masses of stars formed in the present-day universe. These supermassive stars would burn through their nuclear fuel rapidly, exhausting hydrogen fusion in perhaps 1 million years, then collapsing directly to black holes without undergoing supernova explosions, creating intermediate mass black holes as the immediate product of stellar evolution rather than through mergers or growth. Whether such massive stars actually formed in sufficient numbers remains uncertain, depending sensitively on the cooling processes available to primordial gas, on the fragmentation properties during collapse, and on feedback from the forming star that might halt further accretion before sufficient mass accumulates. The runaway collision scenario operates in dense stellar environments where the stellar density becomes so high that physical collisions between stars occur frequently on timescales short compared to the age of the system. In such environments, the most massive star tends to sink to the cluster center through mass segregation, where dynamical friction preferentially removes kinetic energy from more massive objects, causing them to fall toward the gravitational potential minimum while less massive objects move outward to conserve energy. Once concentrated at the center, this massive star collides with other stars passing through the dense core, growing in mass with each merger, potentially triggering a runaway process where the growing central object becomes progressively more massive and more likely to capture additional stars, continuing until it contains a significant fraction of the cluster's total mass. Eventually, this runaway collision product collapses to form an intermediate mass black hole, the final state reached after the central object becomes so massive that no stable stellar configuration can support it against gravitational collapse. Numerical simulations of dense stellar clusters have demonstrated that such runaway processes can operate under appropriate conditions, producing intermediate mass black holes with masses of a few hundred to several thousand solar masses, though the efficiency depends on initial conditions including cluster density, velocity dispersion, and the presence of gas that could dissipate energy and enhance collision rates. The gradual growth pathway involves starting with stellar mass black holes formed through conventional supernovae, then building up to intermediate masses through successive mergers with other black holes or through sustained accretion of gas over millions to billions of years. Black hole mergers release gravitational waves that carry away energy and angular momentum, allowing the merged object to settle into a lower energy configuration, with the final mass equal to the sum of the initial masses minus the small fraction converted to gravitational wave energy. Multiple successive mergers could in principle build stellar mass black holes up to intermediate masses, though this process requires specific dynamical conditions to bring black holes together frequently enough, overcoming the tendency of gravitational encounters to eject rather than capture in low-density environments. Accretion provides an alternative growth mechanism, with black holes gradually accumulating mass from surrounding gas, though this process faces challenges from feedback effects where radiation from the accretion disk heats and drives away nearby gas, potentially limiting accretion rates and extending growth timescales. The combination of mergers and accretion likely contributes to black hole growth across cosmic time, with the relative importance of each mechanism depending on environmental conditions, on the availability of gas and companion objects, and on the detailed physics of accretion flows around black holes of different masses. In the galactic center specifically, simulations indicate that intermediate mass black holes could form through collisional processes within the dense stellar environment, or they might represent the remnants of smaller satellite galaxies that merged with the Milky Way, their central black holes surviving the disruption of their host galaxies and eventually sinking toward the galactic center through dynamical friction. The Milky Way has grown through hierarchical assembly over its history, accreting and merging with smaller satellite galaxies in dozens or hundreds of events, gravitational interactions shredding the satellites and scattering their stars throughout the Milky Way's halo while their central regions sink toward the galactic center. If these satellite galaxies contain central black holes, as theoretical models and observations of dwarf galaxies suggest, those black holes would survive the merger process, becoming embedded in the Milky Way's stellar population and gradually spiraling inward through dynamical friction. This process, where gravitational interactions with surrounding stars transfer momentum and cause massive objects to sink toward the gravitational center, operates more efficiently for more massive objects, explaining how intermediate-mass black holes could reach the galactic center even if the satellite mergers occurred billions of years ago at large distances from the galactic nucleus. Current simulations predict that the Milky Way's galactic center might contain anywhere from 0 to perhaps 10 intermediate-mass black holes depending on the merger history, on the typical masses of black holes in satellite galaxies, and on the efficiency of dynamical friction in delivering them to the central regions rather than leaving them stranded at intermediate radii. The case for GCIRS 13E containing an intermediate-mass black hole rests on several interwoven lines of evidence and theoretical reasoning, beginning with the source's infrared properties and extending through dynamical considerations about its motion and stability. If GCIRS 13E were simply a dust-enshrouded massive star, its infrared luminosity should exhibit variability characteristic of stellar processes, stellar winds, or orbital motion in a binary system, but observations spanning multiple years have revealed relatively stable emission with no clear periodicity or dramatic fluctuations. Massive stars exhibit photometric variability through multiple mechanisms including stellar pulsations where the stellar envelope expands and contracts rhythmically, convective transport in the outer layers creating surface brightness variations, and rotation combined with surface features like spots or asymmetries in the stellar wind producing periodic modulation as the star spins. Binary systems produce additional variability when one star periodically eclipses the other, when tidal interactions between the components induce non-radial oscillations, or when mass transfer from one star to its companion creates episodic brightening events. GCIRS 13E shows none of these characteristic variability patterns in infrared monitoring observations, its brightness remaining constant to within measurement uncertainties over timescales spanning years, suggesting either an intrinsically stable emission mechanism or a configuration where variations average out on short timescales compared to observational cadences. The infrared spectrum itself lacks the molecular absorption bands associated with cool stellar atmospheres or the emission features characteristic of hot circumstellar disks, suggesting that the observed radiation originates from heated dust rather than a stellar photosphere. Cool supergiant stars, which might appear as bright infrared sources even when heavily obscured by circumstellar dust, display strong molecular absorption features from carbon monoxide, water vapor, titanium oxide, and other molecules that form in their extended atmospheres where temperatures drop below a few thousand Kelvin. Hot stars surrounded by circumstellar disks show emission lines from hydrogen, helium, and ionized metals, the emission produced when ultraviolet radiation from the star ionizes nearby gas, which then recombines and cascades down through atomic energy levels while emitting photons at characteristic wavelengths. Neither pattern appears in GCIRS 13E's spectrum, which instead shows only the smooth continuum expected from thermal emission by dust grains distributed across a range of temperatures, each grain radiating approximately as a modified blackbody whose emission peaks at wavelengths determined by its temperature following Wien's displacement law. This dust emission requires a heating source, some central object that deposits energy into the dust either through direct absorption of radiation or through collisional heating by gas, raising the dust temperature to several hundred Kelvin where thermal emission produces significant infrared radiation. Theoretical models propose that an intermediate-mass black hole in this environment would accumulate a small accretion disk or a surrounding envelope of dusty material captured from the ambient interstellar medium and stellar winds, this material heated through viscous dissipation and gravitational compression until it radiates primarily in the infrared, producing exactly the kind of featureless continuum observed in GCIRS 13E. Accretion disks form when material with angular momentum falls toward a central gravitating mass, conservation of angular momentum preventing the material from plunging radially inward, instead causing it to settle into a rotating disk configuration where viscosity transports angular momentum outward and mass inward, allowing accretion to proceed. The viscous stress within the disk generates heat through friction between adjacent layers rotating at different velocities, converting gravitational potential energy into thermal energy that must be radiated away for the accretion to continue. For a black hole of intermediate mass accreting at very low rates, as would be expected in the tenuous environment of the galactic center, the accretion flow likely enters a geometrically thick, optically thin configuration rather than forming a standard thin disk, with the accreting material remaining hot and diffuse, radiating inefficiently, producing more radiation in infrared and radio wavelengths than in X-rays. The dust emission observed from GCIRS 13E could arise from dust grains mixed into this accretion flow or from dust in a surrounding envelope beyond the inner accretion region, heated to temperatures of several hundred Kelvin by the radiation from the inner accretion flow and by occasional heating events when the black hole captures denser clumps of material. The lack of strong X-ray emission, which might seem inconsistent with an accreting black hole, can be explained by the extremely low accretion rate expected in this scenario, with the black hole feeding only on the tenuous surrounding medium rather than stripping material from a companion star, resulting in radiatively inefficient accretion that produces far more infrared than X-ray emission. The ratio of X-ray to infrared luminosity depends sensitively on the accretion rate relative to the Eddington rate, with higher accretion rates producing more efficient conversion of gravitational potential energy to radiation and favoring emission at higher photon energies. At very low accretion rates below about 1% of the Eddington rate, accretion flows enter the radiatively inefficient regime where most of the energy remains in the gas as thermal energy rather than being radiated away, with the gas temperature potentially reaching millions or even billions of degrees but the density becoming so low that the emission measure remains small. Such flows produce relatively little X-ray radiation despite the high temperatures, while infrared emission from surrounding cooler material, heated by the small fraction of energy that does escape as radiation from the inner flow, can dominate the observed spectrum. This scenario matches the observations of GCIRS 13E, which shows significant infrared emission but only weak or undetected X-ray emission, consistent with accretion at rates far below the Eddington limit onto an intermediate mass black hole of several thousand solar masses. The estimated infrared luminosity of GCIRS 13E, a few thousand times the solar luminosity, provides another consistency check on the intermediate mass black hole hypothesis when compared against theoretical predictions for accretion rates and radiative efficiencies. An intermediate mass black hole of 3,000 solar masses has an Eddington luminosity of approximately 4 times 10 to the 38 watts, corresponding to about 100 million solar luminosities, making GCIRS 13E's infrared luminosity only about 10 to the minus 5 times the Eddington luminosity, clearly in the low accretion rate regime. The accretion rate required to produce this luminosity depends on the radiative efficiency, typically parameterized as the fraction of accreted rest mass energy converted to radiation, with values ranging from a few percent for radiatively inefficient flows to 10% or higher for thin disk accretion. Taking a conservative efficiency of 1% suggests that GCIRS 13E's black hole accretes approximately 10 to the minus 6 solar masses per year, equivalent to about 1 Earth mass per year, an extremely low rate consistent with feeding only on the ambient diffuse medium rather than stripping material from a stellar companion. The galactic center environment contains ionized gas at densities of roughly 100 particles per cubic centimeter and temperatures of 10,000 Kelvin, part of the hot phase of the interstellar medium maintained by stellar winds and supernova feedback, providing a reservoir of material that the black hole could accrete through Bondi accretion, where material falling into the black hole's gravitational potential well gets captured and accreted at a rate determined by the density, temperature, and velocity of the surrounding medium. Dynamical arguments strengthen the intermediate mass black hole interpretation by considering how such an object would move through the galactic center environment and how its presence would affect surrounding material and nearby stars. An intermediate mass black hole, unlike a single massive star, possesses sufficient gravitational influence to bind a small cluster of stars to its vicinity, forming what astronomers call a nuclear star cluster or, at smaller scales, a gravitationally bound association of objects that move together through space. The gravitational sphere of influence of a massive object, defined as the region where that object's gravity dominates over the collective gravitational potential of the surrounding environment, scales linearly with the object's mass, meaning that an intermediate mass black hole of 3,000 solar masses has a sphere of influence 3,000 times larger than a 1 solar mass star. In the galactic center environment, where the local stellar density and velocity dispersion create a mean gravitational field, the sphere of influence for such an intermediate mass black hole extends to roughly 0.03 light-years in radius, corresponding to about 600 astronomical units or roughly 15 times the size of the solar system. Within this radius, the black hole's gravity exceeds tidal forces from Sagittarius A** and perturbations from passing stars, allowing it to retain gravitationally bound companions that orbit the intermediate mass black hole specifically rather than participating in the general stellar cluster dynamics. Observations of GCIRS 13E have suggested possible associations with nearby infrared sources, other faint objects that might represent stars orbiting the putative black hole, though the crowded field and observational limitations make such associations difficult to confirm definitively. High-resolution infrared imaging reveals multiple point sources within a few arcseconds of GCIRS 13E, some of which might be foreground or background stars unrelated to GCIRS 13E itself, while others could be genuine members of a compact cluster bound to the intermediate mass black hole. Distinguishing between these possibilities requires multi-epoch astrometric observations to measure proper motions, determining whether candidate companions move coherently with GCIRS 13E or follow independent trajectories, combined with spectroscopic observations to measure radial velocities and search for orbital signatures. The expected velocities for stars orbiting an intermediate mass black hole of 3,000 solar masses at distances of hundreds of astronomical units would be tens of kilometers per second, measurable with current spectrographs but requiring careful analysis to separate orbital motion from the much larger velocities associated with the general galactic center dynamics. If such companions exist and can be confirmed, their orbital parameters would provide direct mass measurements for the central object through application of Kepler's third law, the fundamental relationship connecting orbital period, semi-major axis, and central mass that has been tested and confirmed throughout the solar system and in binary star systems across the galaxy. If GCIRS 13E does contain an intermediate mass black hole with, for instance, 3,000 solar masses, its gravitational sphere of influence would extend to several hundredths of a light-year, large enough to retain gravitationally bound companions but small enough that such a system would appear nearly point-like at the distance of the galactic center. The angular size of this sphere of influence at the galactic center's distance of 8 kiloparsecs corresponds to approximately 2 milliarcseconds, comparable to the diffraction limit of 10-meter-class telescopes in the infrared and potentially resolvable with interferometric techniques that combine light from multiple telescopes to achieve higher angular resolution. Future facilities like the 30-meter telescope or the extremely large telescope may enable direct imaging of the GCIRS 13E system at sufficient resolution to detect individual companion stars within the sphere of influence, revealing the structure of the hypothesized compact cluster and enabling mass measurements through dynamical modeling. The mass-to-light ratio of such a system, defined as the total gravitating mass divided by the total visible luminosity, would greatly exceed typical values for stellar populations if the central object is indeed a black hole, because the black hole contributes mass without contributing light, shifting the mass-to-light ratio toward higher values characteristic of systems dominated by compact objects rather than normal stars. The velocity of GCIRS 13E, measured through infrared astrometry over multiple epochs, shows the object moving on what appears to be an elongated orbit around Sagittarius A*, consistent with expectations for a massive object that has not yet fully relaxed into a circular orbit through dynamical friction. Theoretical calculations indicate that an intermediate mass black hole injected into the galactic center, whether through galaxy merger or cluster infall, would gradually spiral inward over timescales of millions to tens of millions of years, losing orbital energy through gravitational interactions with surrounding stars, a process whose current stage might be observable in objects like GCIRS 13E. Dynamical friction operates through the cumulative effect of many weak gravitational encounters between the massive object and the background stellar population, each encounter transferring a small amount of momentum and energy but the integrated effect over many encounters causing significant orbital evolution. The timescale for dynamical friction depends on the ratio of the massive object's mass to typical stellar masses, on the density and velocity distribution of the background stellar population, and on the orbital parameters of the massive object itself. For an intermediate mass black hole orbiting at half a light-year from Sagittarius A*, Current estimates suggest dynamical friction timescales of 10 to 50 million years to spiral into the central regions, short compared to the galaxy's age but long enough that multiple such objects could remain at various stages of inspiral, creating an observable population of intermediate mass black holes at different distances from the supermassive black hole. The orbital energy and angular momentum of GCIRS 13E, inferred from its position and velocity, place it on a trajectory that likely originated at larger radii within the galaxy, suggesting that this object has migrated inward from beyond the central parsec, whether through dynamical friction following a galaxy merger or through gradual evolution within the galactic center environment itself. Objects on circular orbits at the galactic center maintain constant orbital radii indefinitely in the absence of perturbations, while objects on eccentric orbits experience varying gravitational interactions depending on their instantaneous distance from Sagittarius A*, with friction strongest at periastron where the stellar density and encounter rate both peak. This differential friction causes eccentric orbits to gradually circularize while simultaneously shrinking in size, a process that eventually delivers the object to the innermost regions where it merges with the central supermassive black hole. The current orbital parameters of GCIRS 13E, if it indeed contains an intermediate mass black hole, encode information about when the object entered the galactic center region, about what interactions it has experienced during its inward migration, and about how long remains before the final merger occurs. Questions that detailed numerical simulations can address by evolving model systems forward in time and comparing outcomes against observations. The measurement uncertainties in GCIRS 13E's current position and velocity propagate into substantial uncertainties about the orbital history and future evolution, requiring continued monitoring to refine orbital parameters and reduce these uncertainties, gradually narrowing the range of plausible formation and evolution scenarios. Alternative explanations for GCIRS 13E's properties must be considered and evaluated against the available observations, ensuring that the intermediate mass black hole hypothesis represents the most plausible interpretation rather than an exotic possibility favored over simpler alternatives. One competing explanation proposes that GCIRS 13E could be an extremely young massive star still embedded in its natal cocoon of dust and gas, its stellar light completely absorbed by surrounding material and re-radiated in the infrared. Star formation in the galactic center environment appears challenging because of the intense tidal forces from Sagittarius A** and the disruptive effects of stellar winds from massive stars, but observations have confirmed the presence of relatively young massive stars within the central parsec, indicating that star formation can occur despite these hostile conditions. These young massive stars, some with ages of only a few million years based on their spectral properties and positions on theoretical evolutionary tracks, likely formed in a disk of gas that orbited Sagittarius A** several million years ago, fragmented into dense clumps that collapsed to form stars, with the disk subsequently dispersing through photoevaporation by the intense ultraviolet radiation from the newly formed massive stars. If GCIRS 13E represents a very young massive star still enshrouded in its formation environment, the infrared emission would arise from dust heated by the central star's radiation, with the dust optical depth sufficient to completely extinguish the stellar light at shorter wavelengths while allowing infrared photons to escape after multiple scatterings through the dusty envelope. However, the lack of spectral features characteristic of young stellar objects, the absence of molecular emission from surrounding gas, and the stability of GCIRS 13E's infrared emission over many years argue against this interpretation. Young stellar objects typically show rich infrared spectra including emission from polycyclic aromatic hydrocarbons, from water ice, from silicate dust features at wavelengths near 10 micrometers, along with molecular emission lines from carbon monoxide, water vapor, and other species in the surrounding gas. These spectral signatures arise because the dust and gas around young stars span a wide range of physical conditions, with temperatures ranging from tens of Kelvin in the outer envelope to thousands of Kelvin near the stellar surface, producing characteristic spectral features that serve as diagnostics of the physical state and chemical composition. GCIRS 13E lacks these features, showing only the featureless continuum characteristic of warm dust without the additional complexity expected from an active star formation site. Young massive stars also drive powerful stellar winds and produce intense ultraviolet radiation that ionizes surrounding gas, creating regions of ionized hydrogen that emit strongly in hydrogen recombination lines, these emission features serving as unmistakable signatures of massive star formation when present. Again, GCIRS 13E shows no evidence for such emission, suggesting either that it is not a young massive star or that some special circumstances suppress the expected spectral features. Another possibility suggests that GCIRS 13E might be a close binary system containing two massive stars or a stellar mass black hole accreting from a companion, the system's combined properties producing the observed infrared signature. Binary systems are common among massive stars, with observations suggesting that the majority of massive stars form in binary or multiple systems rather than as isolated single stars, making binarity a natural explanation to consider for any unusual stellar source. In a close binary system where both components remain embedded in a common dust envelope, the combined luminosity from both stars heats the surrounding dust, producing infrared emission similar to what a single more luminous star would generate, potentially explaining GCIRS 13E's infrared luminosity without requiring an intermediate mass black hole. If one component in the binary is a stellar mass black hole accreting from its companion, the accretion luminosity adds to the stellar luminosity, potentially producing distinctive spectral features including hard X-ray emission from the inner accretion disk and optical emission lines from the outer disk regions. Such systems, known as high-mass X-ray binaries elsewhere in the galaxy, typically show strong variability as the binary orbital motion modulates the accretion rate and as structures in the accretion disk rotate around the black hole, producing periodic or quasi-periodic brightness changes on timescales from milliseconds to days depending on the binary parameters and accretion geometry. The specific observational characteristics of GCIRS 13E, particularly its lack of variability and its peculiar spectral properties, seem inconsistent with standard binary scenarios. Close binary systems containing massive stars show photometric variability through ellipsoidal variations as the tidally distorted stars present different cross-sections to the observer during orbital motion, through eclipses when one star passes in front of the other, and through reflection effects where radiation from one star illuminates and heats the facing hemisphere of its companion. High-mass X-ray binaries show dramatic X-ray variability and strong X-ray emission that should be detectable even through the extinction toward the galactic center, yet GCIRS 13E remains faint or undetected in X-ray observations, suggesting that if it contains a stellar mass black hole, the accretion rate must be extraordinarily low, below typical values for systems where accretion produces observable signatures. The stability of GCIRS 13E's infrared emission over monitoring timescales spanning years also argues against binary scenarios, because binary orbital periods for closed systems span days to months, short enough that multiple orbital cycles should be observed during multi-year monitoring campaigns, producing periodic variability that would be detectable in the infrared light curves if the binary interpretation were correct. A third alternative proposes that GCIRS 13E represents a small molecular cloud or dust concentration illuminated and heated by the intense radiation field of the galactic center, but such structures would be expected to show far more complex morphology and would likely be shredded by tidal forces on relatively short timescales, making their persistence over observational epochs difficult to explain. The galactic center environment contains numerous small gas and dust clouds, fragments of larger molecular structures that have been disrupted by tidal forces, by stellar winds, by supernova explosions, and by other violent processes. These fragments visible in infrared and radio observations as compact or filamentary structures with characteristic spectral signatures including molecular emission lines and thermal dust continuum. If GCIRS 13E were such a cloud, its infrared emission would arise from dust heated by the ambient radiation field, with dust temperatures determined by the balance between radiative heating from nearby massive stars and cooling through infrared emission. However, dust clouds in the galactic center typically show spatially extended morphology when observed at high resolution, revealing internal structure and elongation caused by tidal stretching, characteristics that GCIRS 13E does not display in available imaging observations, where it appears point-like at the resolution limit of current instruments. Additionally, isolated dust clouds without internal self-gravity would be disrupted by tidal forces from Sagittarius A** on timescales of thousands to tens of thousands of years, calculated by comparing the tidal force across the cloud's diameter against the cloud's internal pressure support, predicting that such clouds should disperse rapidly unless some mechanism confines them, such as magnetic fields or gravitational binding to an embedded massive object. Further alternatives involving exotic stellar configurations, unusual chemical compositions, or rare evolutionary states can be conceived but generally require fine-tuning of parameters or invoke phenomena not observed in other astrophysical contexts, reducing their plausibility compared to explanations involving known physical processes and object types. The scientific method demands consideration of all plausible explanations, evaluation of each against available observations, and preference for hypotheses that require fewer ad hoc assumptions and that connect to broader theoretical frameworks supported by evidence from other systems. The intermediate mass black hole interpretation for GCIRS 13E, while exotic in the sense that intermediate mass black holes remain poorly observed and confirmed, connects naturally to theoretical predictions about black hole formation and growth, explains the full range of observational properties without requiring special circumstances or fine-tuning, and makes testable predictions about companion objects and dynamical behavior that future observations can verify or refute. Alternative explanations face challenges in explaining one or more aspects of the observational constraints, whether the lack of spectral features, the absence of variability, the faint X-ray emission, or the apparent point-like morphology, though none can be definitively ruled out without additional observations that further constrain the system's properties. The broader context of intermediate mass black holes in galactic centers provides important perspective for evaluating the GCIRS 13E hypothesis, connecting this individual case to larger questions about black hole formation, growth, and demographic distributions across cosmic history. Supermassive black holes like Sagittarius A** pose something of a formation puzzle, their masses of millions to billions of solar masses requiring either extremely rapid growth from stellar mass seeds or formation through direct collapse of massive gas clouds in the early universe. The problem becomes particularly acute when considering observations of quasars at very high redshifts, seen as they existed when the universe was less than 1 billion years old, revealing supermassive black holes already in place with masses exceeding 1 billion solar masses despite the limited time available for growth since the Big Bang. Starting from a stellar mass black hole of 10 solar masses and accreting at the Eddington limit continuously, the maximum sustainable accretion rate where radiation pressure balances gravitational infall, produces an exponential growth in mass with an e-folding time of approximately 45 million years. Growing from 10 solar masses to 1 billion solar masses at this maximum rate requires approximately 200 million years, accounting for roughly 5 e-folding times to span the factor of 100 million increase in mass, barely sufficient time if accretion begins immediately after the first stars form but requiring continuous accretion at or near the Eddington limit without interruption, a condition that seems unlikely given feedback effects and the episodic nature of gas supply in realistic astrophysical environments. Intermediate mass black holes could play a crucial role in this growth process, serving as the seeds that eventually develop into supermassive black holes through successive mergers and accretion episodes. If the first black holes formed with masses already in the hundreds or thousands of solar masses rather than starting from stellar mass remnants, the required growth factors decrease by corresponding amounts, easing the timing constraints and allowing more realistic accretion histories with periods of high and low activity, with interruptions when feedback clears away surrounding gas, with variations in accretion rate as environmental conditions change over time. In this picture, galaxies in the early universe contained multiple intermediate mass black holes formed through various pathways, these objects gradually coalescing as their host galaxies merged, building up the central supermassive black hole through hierarchical assembly. Each merger between two intermediate mass black holes produces a larger intermediate mass black hole, with mass equal to the sum of the merging components minus the few percent radiated away as gravitational waves, continuing until the accumulated mass reaches supermassive scales. Simultaneously, gas accretion adds mass continuously when environmental conditions provide sufficient fuel, with the relative contributions of mergers and accretion to total growth depending on the merger history of the host galaxy, on the efficiency of gas transport to the galactic center, and on feedback processes that regulate star formation and black hole feeding. Galactic centers like that of the Milky Way might still contain remnant intermediate mass black holes that have not yet merged with the central supermassive black hole, objects like GCIRS 13E that represent late stages in this coalescence process, their eventual inspiral and merger contributing incrementally to Sagittarius A**''s continued growth. The presence of these remnant objects provides a test of hierarchical assembly models, with predictions about how many such objects should remain at various distances from the supermassive black hole, about their mass distribution spanning from hundreds to tens of thousands of solar masses, and about their orbital properties reflecting their formation mechanisms and subsequent dynamical evolution. Numerical simulations of galaxy formation and evolution have begun to make detailed predictions about intermediate mass black hole populations in galactic centers, tracking black holes through cosmic time as galaxies merge and evolve, following orbital decay through dynamical friction, accounting for gravitational wave emission during the final merger phases. These simulations predict that typical galaxies like the Milky Way should contain anywhere from 0 to several intermediate mass black holes in their central regions, with the exact number depending sensitively on the poorly constrained efficiency of dynamical friction, on the masses of black holes in satellite galaxies, and on whether satellite galaxies retain their central black holes during tidal disruption or whether those black holes are stripped away and lost before reaching the galactic center. The detection and characterization of intermediate mass black holes in the Milky Way's galactic center would provide crucial calibration for these theoretical models, constraining parameters that currently span wide ranges of uncertainty, enabling more confident predictions about black hole populations in other galaxies throughout the universe. If GCIRS 13E and similar objects prove to contain intermediate mass black holes, their observed properties including masses, orbital parameters, accretion rates, and environmental effects inform theoretical models about how these objects behave in dense stellar environments, how they interact with surrounding stars and gas, how long they survive before merging with the central supermassive black hole. The statistical properties of the population, if multiple intermediate mass black holes can be identified and characterized, reveal information about the merger history of the Milky Way, about the typical masses of black holes in dwarf galaxies and satellite systems, about the efficiency of processes that deliver these objects to the galactic center. Even negative results, finding fewer intermediate mass black holes than predicted, provide important constraints that would require modifications to formation models, to assumptions about merger rates, or to estimates of dynamical friction efficiency. Observational strategies for confirming or refuting the intermediate mass black hole nature of GCIRS 13E require pushing the capabilities of current and future astronomical facilities to their limits, combining high-resolution imaging, precise astrometry, and sensitive spectroscopy across multiple wavelengths. The most direct confirmation would come from detecting stars orbiting GCIRS 13E specifically, their velocities and orbital parameters revealing the central mass through standard Keplerian mechanics, just as the S-star's orbits have confirmed Sagittarius A**'s mass. Such observations demand extraordinary angular resolution to resolve individual stars within what may be a small cluster around GCIRS 13E, along with multi-epoch measurements spanning years or decades to trace orbital motion. Adaptive optics systems on 30-meter class telescopes now under construction, combined with infrared interferometry techniques, may provide sufficient resolution to detect such companions if they exist. Spectroscopic observations at higher sensitivity could reveal subtle emission or absorption features that would discriminate between alternative explanations, perhaps detecting accretion disk signatures characteristic of black holes or stellar features indicating a conventional star. Radio observations using very long baseline interferometry could potentially detect compact radio emission from the immediate vicinity of an intermediate mass black hole, though the expected emission levels remain uncertain and likely very faint. X-ray observations during periods when GCIRS 13E might accrete material from a passing gas cloud or stellar wind could reveal flares or variability that would confirm active accretion onto a compact object, providing complementary evidence beyond the steady infrared emission. The eventual fate of GCIRS 13E, if it does contain an intermediate mass black hole, involves a gradual spiral toward Sagittarius A** driven by gravitational wave emission and dynamical friction, a process that will culminate in a merger event whose gravitational wave signature may be detectable by future space-based observatories. As the intermediate mass black hole orbits through the galactic center, its gravitational interactions with passing stars transfer momentum and orbital energy, causing the object to gradually lose angular momentum and spiral inward along a decaying orbit. This dynamical friction process operates more efficiently for more massive objects, meaning that an intermediate mass black hole experiences stronger drag than individual stars, accelerating its journey toward the supermassive black hole. Theoretical calculations suggest that an object like GCIRS 13E, if it contains several thousand solar masses located half a light-year from Sagittarius A*, would merge with the central black hole within 10 to 100 million years, a timescale short compared to the galaxy's age but long compared to human observation timescales. As the intermediate mass black hole approaches closer to Sagittarius A*, gravitational wave emission becomes increasingly important, the orbital energy radiated away as ripples in spacetime that propagate outward at light speed. The final stages of the merger, when the two black holes orbit each other at distances comparable to their Schwarzschild radii, would produce gravitational waves at millihertz frequencies, precisely the range targeted by proposed space-based detectors like LISA, the Laser Interferometer Space Antenna. Detecting such a merger would provide unprecedented insight into the properties of both black holes, measuring their masses and spins with extraordinary precision, testing general relativity in the strong field regime, and confirming the existence of intermediate mass black holes as a distinct population. Beyond GCIRS 13E specifically, the question of intermediate mass black holes in the galactic center extends to the possibility that multiple such objects inhabit the region, some already identified as infrared sources with peculiar properties, others potentially hidden within the observational confusion of the crowded stellar field. Statistical studies of infrared sources in the central parsec have identified several other candidates with properties similar to GCIRS 13E, objects showing featureless infrared spectra, lack of clear stellar features, and dynamical characteristics suggesting higher masses than typical stars. If the galactic center does contain a population of intermediate mass black holes, their collective presence would have profound implications for the region's dynamical evolution, the structure of the stellar cluster, and the growth history of Sagittarius A star. Theoretical simulations suggest that the presence of multiple intermediate mass black holes would affect the stellar velocity distribution, creating dynamical signatures potentially detectable through careful analysis of stellar proper motions and radial velocities. These objects would also influence the distribution of stellar mass black holes, which are expected to be abundant in the galactic center but largely invisible because they do not accrete brightly, their presence inferred indirectly through dynamical modeling. The interactions between intermediate mass black holes and stellar mass black holes, along with the gradual merger cascade as objects of various masses coalesce, would shape the galactic center's evolution over cosmic time, leaving imprints on the current configuration that careful observations might reveal. The scientific significance of confirming intermediate mass black holes near Sagittarius A** extends beyond the galactic center itself to fundamental questions about black hole formation throughout the universe, the assembly of galaxies through hierarchical mergers, and the gravitational wave background that permeates spacetime. If intermediate mass black holes prove to be common in galactic centers, they provide a natural explanation for how supermassive black holes formed so rapidly in the early universe, with the seed black holes already containing thousands of solar masses rather than starting from stellar mass remnants. This formation pathway would predict specific relationships between black hole masses and host galaxy properties, correlations that observational surveys can test by measuring supermassive black hole masses across diverse galaxy types and comparing them to theoretical predictions. The merger history of intermediate mass black holes with central supermassive black holes throughout cosmic time would contribute to the stochastic gravitational wave background, a diffuse signal produced by the superposition of countless merger events at various distances and epochs. Current and future gravitational wave observatories seek to detect this background, whose amplitude and frequency spectrum encode information about the black hole merger rate throughout cosmic history. The detection of even a single intermediate mass black hole merger near Sagittarius A*, whether from GCIRS 13E or another object, would calibrate models of how common such events are, allowing astronomers to predict the gravitational wave background's properties more accurately and to understand how typical our galactic center is compared to others throughout the universe. At the boundary of current observational capabilities and theoretical understanding, GCIRS 13E represents both a specific astronomical puzzle and a window into broader cosmic processes, an object whose true nature remains uncertain but whose implications would reshape understanding if the intermediate mass black hole interpretation proves correct. The technical challenges of observing this faint infrared source in one of the most crowded and obscured regions accessible to astronomy demonstrate the limits of current technology and the need for next-generation facilities that can peer deeper, resolve finer details, and measure with greater precision. The theoretical frameworks used to interpret GCIRS 13E's properties draw on multiple subfields of astrophysics, connecting stellar dynamics, accretion physics, general relativity, and galaxy formation into an integrated picture of how matter behaves in the universe's most extreme gravitational environments. As observations continue, as new data accumulates from improved telescopes and novel observational techniques, the mystery of GCIRS 13E will gradually resolve toward clarity or perhaps deepen into new puzzles that current thinking cannot anticipate. The half-light year that separates this enigmatic object from Sagittarius A** represents both a vast distance on human scales and a cosmically intimate proximity, a gap that will close over millions of years if gravitational physics proceeds as theory predicts, eventually delivering whatever mass GCIRS 13E contains into the supermassive black hole's gravitational embrace, adding incrementally to the 4 million solar masses already accumulated there, continuing the process of hierarchical assembly that has shaped galactic centers since the first structures emerged from the primordial cosmos, a process that continues in the present epoch, observable in principle if not yet confirmed, suggested by the properties of this peculiar infrared source that may, or may not, harbor one of the universe's most elusive objects, an intermediate mass black hole poised at the edge of detection, occupying the space between theoretical prediction and observational confirmation, waiting for the next generation of instruments to reveal its secrets or overturn current interpretations in favor of explanations not yet imagined.